it'll tell you, for some given amount of mass, the size of the volume you need to pack it in to make a black hole. For example, if you wanted to make a black hole out of the Earth, you need to pack the entire thing into a volume about the size of a blueberry. Most black holes we know of are much larger than apples or blueberries, of course. The black hole at the center of our galaxy has a diameter equivalent to about 1/3 of the distance between the Earth and the Sun, but with a mass 10 million times that of the Sun. And there are black holes much larger than that in other galaxies, with masses tens of billions of times that of the Sun, and with volumes that would encompass our entire solar system. So this is all very well and good, but how do black holes come into existence? How does the universe make something so dense that it nearly punctures the fabric of space-time? Well, one way is when an enormous star dies. After billions of years, a star can exhaust the fuel it needs to burn, and in one final hurrah, explode. It's supposed to explode, I don't know what's going on. I think some of the animations got ruined here. This is really unfortunate. See if I can try this again. Nope, not gonna work. So in one final hurrah, explodes. And with no more gravity to push it outward, with no more nuclear reactions to push it outward, gravity wins, and the whole thing collapses in on itself. And this collapse could be so severe that it creates a black hole. So you can see that it takes a pretty violent event, like an enormous star dying, to make a black hole. So is it possible that we can make black holes where I work, at the Large Hadron Collider at CERN? The Large Hadron Collider is a 27-kilometer circular tunnel on the border of France and Switzerland. And in this tunnel, we take tiny particles and we accelerate them to almost the speed of light. And then we smash them each into each other at the highest energies that humans have ever used in such an experiment. This is also not working. It's supposed to be a little bit of a clip here. I think we got the wrong file. Experiment. At the smallest possible level, as you'll see in a moment here, these collisions are a pretty violent event. And it's theoretically possible that we could make tiny modified versions of black holes that would evaporate immediately. This would be phenomenal, despite the looks on some of your faces, because the real reason we physicists are obsessed with black holes is that they can help us answer one of the most baffling and long-standing questions in science: the mystery of how gravity and quantum mechanics work together. In physics, we have two fantastically good theoretical models that have withstood essentially all of our experimental tests. The first is called general relativity, which describes how gravity works on very large scales. The other is called quantum mechanics, which describes the world of the small. Each of these by itself ranks among the most impressive intellectual achievements of humankind. But there's a problem. When we try to naively combine these two theories, hoping for a more fundamental theory of the universe, everything breaks. We get nonsense answers like infinite energies or probabilities greater than 1. When this happens, this is the universe's way of telling us to think harder. We suspect that far back at the moment of the Big Bang, some kind of quantum gravity must have existed. And in the current universe, the place where these two theories collide is in a black hole. So studying a black hole up close in the laboratory would shed monumental light on the subject. Alas, we see no evidence of miniature black holes at the Large Hadron Collider yet. But maybe we just need a bigger and more energetic collider. Discussions are currently underway for the potential successor to the Large Hadron Collider, the Future Circular Collider. Presumably they'll change the name when the future becomes the present, which would be 100 kilometers around and could reach energy 7 times that currently achieved. But would that be big enough? Maybe quantum gravity is waiting for us on the moon, where the Large Hadron Collider is 27 kilometers around. A collider encircling the moon would be 11,000 kilometers around and could reach energies 1,000 times that currently achieved. So let's recap. I'm standing in front of you and I'm telling you we should build a collider that encircles the entire moon sometime in the 22nd century to make black holes. Am I crazy? Well, after talking about this concept for several years in a kind of inspirational, sort of rough, vague way, just last year, a colleague and I actually wrote a paper about this prospect, and it turns out it's not crazy. There are no showstoppers to building a collider around the moon. All the scientific and technological concepts are there. It's just a matter of development and scale. A circular collider on the moon sometime in the 22nd century might seem impossible, but it's not impossible. It's regular impossible. And regular impossible we can do. Regular impossible is only impossible right up until the moment someone makes it possible. But will that be big enough? I like the way you think. No. The larger the collider, the higher the energy until you reach a kind of an ultimate energy known as the Plunk energy, Max Planck. The Plunk energy, and this is the energy at which gravity and quantum mechanics must have something to do with each other. However, by some naive estimates, to reach the Plunk energy in a collider, we would probably have to build one like the Large Hadron Collider that circles around the outer orbit of Neptune, and I see that this has been nicely ruined here in translation. So the blue line is supposed to very dramatically appear past Neptune. Imagine that's what happened instead. Clearly, we're going to need some major innovation to make such a collider happen. And by that time, our civilization, once it's finally advanced enough to build such a superstructure, will probably have advanced enough to master interstellar space travel. And at that point, 500 years from now, you will be in your spaceship traveling to a black hole. One day, in your ship, you get tired. You note that you should arrive at your destination in about 12,000 years. So you decide to take a 12,000-year-long nap. And as you lie down in your cryogenic bed, you very slightly bump your ship's accelerator. You don't even notice. After 12,000 years, you awake, fix yourself a cup of coffee, and you notice from your gravitational sensor that something is very wrong. You seem to be too close to the event horizon of your black hole. You look out the window and you see an enormous, profoundly black disk in space. The light from the stars and galaxies behind it twisted and deformed. You stare into the center of this disk, a cosmic eye staring back at you, and it's the emptiest thing you've ever seen. Your jaw drops and your eyes widen, and then you realize that you're not sure if you've passed the event horizon, the point of no return, yet. You double check your gravitational sensor and it says you're not there yet. You have 5 seconds to blast away. You leap from your chair, leaping toward the controls for your rockets, spilling hot coffee all over your hands. You scream and fall to the ground, and by the time you get up, it's too late. You're passing the event horizon of a black hole. You nearly stop breathing. Your mouth feels like sand. You close your eyes. You can't believe that this could possibly be happening. You open your eyes and look out the window again, and everything looks about the same. The ominous black disk is getting a little larger maybe, but otherwise you don't feel any different. You feel the same. You think maybe your estimate was wrong. Maybe there's still a chance to escape. You triple check your gravitational sensor and it says that no matter which direction you point it, you are pointing toward the center of a black hole, and then you know for sure. You've passed the event horizon. You are inside a black hole? a calm terror settles over you. How did you get in this situation? For years, while you were asleep, the conditions of the universe around you were changing, nearly imperceptibly, and then suddenly, it was too late. Floating in your spaceship inside of a black hole, what do? You might start thinking of possible escapes. I mean, maybe it's possible that all the clever scientists were wrong, and there's some way to escape that hadn't been anticipated. You start fantasizing that maybe if you just get lucky or you just wait long enough, the situation will sort itself out, and you will eventually pass back over the event horizon and could zoom away from the black hole, back to the universe you once knew, back to the way things were. And as you're fantasizing, you look down and you see that your shoes are floating away from you, and your legs are being stretched into long, thin, spaghetti-like strands. And then suddenly, your feet are so far away that you can't see them anymore. And in that split second, before you reach the center, you realize two things. One, that no one really knows what happens in the center of a black hole. And two, there is no going back to the way things were. The only way out, if there is a way out, is directly through the black hole. Sometimes reality becomes twisted, seemingly beyond recognition. And right now, as the planet burns and the global temperature rises, and as large-scale war waged by a fascist has returned to Europe for the first time in almost 80 years, and as so many of our fellow humans are dead because of a mismanaged pandemic, while so many others allow themselves to be duped by pseudoscience, disinformation, right now, you'd be forgiven for thinking that we'd fallen into a societal black hole. In retrospect, it happened so slowly, nearly imperceptibly, while so many of us were asleep. And then it was too late. But just like in a black hole in space, the only way out is through. Our current societal black hole is a golden opportunity to construct a better world and to think in radical new ways to do so. But we can't be superficial. We can't think incrementally. We have to dig deep, and we have to think big. Question the fundamentals, and we have to think big. For example, there's more than one reason why we should consider building a particle collider on the moon. The first reason is scientific. Such a project would teach us incredible things about the universe, full stop. But the second reason is existential. Our society is addicted to repeating its mistakes. And right now, we seem to be on the verge of simply giving space and Mars and the moon to wealthy private individuals and corporations whose only interests are extraction, exploitation, and profit. This is bad. Because this extractive mindset here on Earth has led to the destruction of the environment due to anthropogenic global warming. If we simply repeat the same mistakes in space that we've made here, that's bad. So projects like a circular collider on the moon, projects mounted solely because our species is curious about the universe, and it doesn't have to be a collider, there's lots of other scientific projects. Centering such projects would remind the world that the moon belongs to everyone, instead of encouraging a moon rush where wealthy private individuals or private interests compete to see who can be the first to extract moon minerals or who can be the first to build a luxury lunar wellness spa for billionaires. the moon should be protected in perpetuity against commercial exploitation. And big thank you. And century projects like this, projects mounted solely because our species is curious about the universe, would remind us, as I said, the moon belongs to everyone. But dig deeper, think even bigger, question even those fundamentals, just like the first people 100 years ago who finally realized, more than 100 years ago, finally realized that space was not empty, not the thing that we thought it was. The problem we face now is not just a few narcissistic billionaires. Why do billionaires even exist to begin with? How did we allow ourselves to develop and maintain systems that result in a few dozen individuals holding as much wealth as billions of the rest of us combined? And why do we allow the beneficiaries of these systems to convince us that such systems are inevitable, as if they're laws of physics? Keep in mind, gravity creates black holes, and gravity is simply a law of nature. But the social, political, and economic structures that lead to extreme wealth inequality, racist policing, the climate emergency, are not laws of nature. They're human-made, which means they can be human, unmade. We owe it to future humans to finally find the courage to unmake these structures, because of course it won't be you 500 years from now traveling to a black hole. It's up to us to ensure that the Earth itself and our society are not crushed into oblivion. And it's up to us to fix our social inequities so that your great 25 greats granddaughter can push forward into the unknown to better understand humanity's place in this vast universe. Thank you.
I don't know where it is right now, but it's spinning after this. I want to make a little Q&A with the audience if they have any questions, but first of all, I have some questions.
I'm thinking my water while you ask my
question.
Do. You think about what a black hole is. Again, this is only about 25 minutes or so, I can't go into all the details. But a black hole is actually just another physical object. Like from science fiction, we often get this idea that it's like, the black hole, there's these voracious things that suck in everything around it. From a certain distance, if you stay far enough away, a black hole is just another gravitational object. It's just another thing that sits there. So you can think of it this way, like I said that if you want to make the black hole out of the Earth, you have to pack it into something the size of a blueberry. So if we spontaneously did that right now, we can't do this at CERN, by the way, don't worry. That if we spontaneously did that, what would happen to, say, the moon? From science fiction, you might think, oh no, there's a black hole, the moon is going to get sucked in or something. No, the moon right now is in a totally perfect, stable orbit with the Earth, but the Earth is just this particular fixed mass gravitational object. It doesn't matter how large it is. If it suddenly turned into a tiny object, like a little black hole, the moon wouldn't even care. It would just keep going just the way it did before. It wouldn't get sucked in, no problem at all. So if that's the case, then yes, you can have miniature black holes, which is just another, it's some amount of mass, it's just in a very small, volume. You could fall into a black hole, yes.
But that wouldn't affect, how would it affect the black hole which falls into the black hole? Would it become part of a bigger black hole, or?
In fact, they can merge. So who here has heard of gravitational waves? I gotta see all these hands. You've all heard of gravitational waves. Yes, okay. So the first gravitational wave that was announced to be detected in 2015, I want to say, this was in fact a gravitational wave that was evidence from two black holes that had actually merged together. So we know that this is kind of what you're saying when a black hole falls into another black. I think these were roughly the same mass. but basically they had been going around each other for a long time and eventually sort of merged. So yeah, black holes can fall into one another.
Fascinating. Will it ever be possible, I mean, now I'm coming from a science fiction point of black hole view, but will it ever be possible to like control black holes, to be able to use them as, I don't know, are they usable in any way?
That is a very, very good question. From a science fiction perspective, I would like to say yes, because there has been a lot of really good speculative fiction that is based upon pretty good science. Except when I say that yes, I have to have both. I have to give a caveat, right? I have to put on my hat of the kind of current sort of sober, rational scientist. It's like, well, no, it seems impossible for our species to do that, But for the kind of like speculative, because the thing is that I'm attracted to the very edges of human knowledge. That's what I've been my whole life. That's why I'm a particle physicist, right? Particle physicist is the kid who never accepted, oh, that's just the way it is as an answer for anything. And so, for example, if you ask, ask your dad, why is the sky blue? Your dad kind of bullshits or something, and then he says, well, I don't know, that's just the way it is. For some kids, they're like, whatever, and then they go and play. But for the physicists, they're like, that's not satisfying. And they'll go and ask somebody else, and then they'll get to different sciences, and then you get to biology, and you ask what's smaller than that. And you get to chemistry, what's smaller than that? You get to physics, what's smaller than an electron? And the answer is we don't know. That's where I want to be. That's where my brain goes. So I'm really addicted to the kind of edges, the borderlands of science. And right now, one of the things with the borderlands of science is what's inside of a black hole. One of the possible, I promise I'm answering your question. One of the possible solutions to what happens inside of a black hole, you might notice that I never actually say what's in a black hole here. One of the possible mathematical solutions to a black hole is that you in fact can have something that everyone's heard of called a wormhole, right? So this is a wormhole, shows up in movies like Interstellar you mentioned earlier. In physics we refer to this as an Einstein-Rosen bridge. And these wormholes could, in principle, be little connectors from one part of the universe in space-time to another part of our universe in space-time, possibly far back in time, probably not, but more likely farther in the future, and also another completely different part of space. Or, in principle, these could be little wormholes to other universes. These are all completely scientifically valid conclusions from the mathematics of general relativity. Of course, we have no evidence that any of them exist right now, but it is a possibility. So, the way to answer your question is that probably not, but maybe if we were able to somehow determine that these Einstein-Rosen bridges exist, that wormholes actually exist, and we were able to somehow create a black hole in the laboratory that was sort of like human-sized, and then you could like control it and choose where it goes in the universe. All of these are very tall orders, so I have to say no with a kind of big maybe, or I also have to say yes with a but.
All right. Okay, that's perfectly fine for me. So, do we have any questions in the audience? Someone to...
Very much. That was interesting.
Highest compliment for a scientist.
From a German, yes. This may be right or wrong, but as a layperson, I know that we expect physics, we hope for physics to have a breakthrough, a notable, significant breakthrough, ideally every 30 years. Have we had one, in your opinion, and if so, which one is it? And if we haven't, what are you hoping most for?
That's a very good question. So I don't necessarily ascribe to the idea that there's kind of this scientific progress goes in this kind of clockwork way, every 30 years or so. You can kind of, depending on how you squint at history, you can convince yourself, and how you classify discoveries, you can convince yourself that that's kind of the way it works. But we're also at a point in time for physics especially, that this is getting more and more difficult to be able to predict what's going to happen next. I'll give you the reason is this. So the most recent huge breakthroughs in physics, right, the big discoveries, in terms of experimental discoveries, have been imaging a black hole, like I just mentioned here, this discovery of gravitational waves. And the discovery of gravitational waves really is one of the most remarkable things ever, because it's basically a brand new way for us to look at the universe that did not exist before. So that's fantastic. And then the third one is the discovery of the Higgs boson particle by my colleagues and I in 2012. Yeah, don't worry, it was like 6,000 people discovered the Higgs boson, so don't worry. So these things are really, really big steps forward. However, they are all more or less things that were predicted a long time ago, right? So as you're kind of maybe you're intimating is, a lot of times in physics, and especially in particle physics and astrophysics, the history of the 20th century physics was basically this wonderful interplay, this kind of dance between theoretical physics and experimental physics. So theorists, of course, are those that occupy themselves with the math all day long and the kind of concepts, and they come up with things. Wait a minute, if this were true, that would explain X, Y, Z, and it also predicts PQR, blah, 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 so you can go and test that. And then this happened like clockwork through the 20th century, right? It's like so-and-so thing was predicted, and then it was discovered and verified. And that made another weird kind of and then the theorists explained that and said, oh, you should also find this, and that was found, blah, 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 all the way up to and including the Higgs boson particle. But that's it. So as it stands now, we're really at an interesting crossroads, in my field especially, but physics in general, because we have this fantastically good theoretical model of the way that our universe works at its smallest possible scales, and it's called the Standard Model of Particle Physics, capital S, capital M. It's this wonderfully remarkable thing that basically has satisfied all of our experimental tests, and the last remaining prediction of that thing was the Higgs boson particle. However, we know for a fact that the Standard Model is not the complete story. It does not contain gravity, okay? And I know that gravity exists. I'm sitting in my chair here, right? It does not contain dark matter. Each one of you has about 1 billion particles of something called dark matter flowing through your body every second. We don't know what that is, and it's not in the Standard Model. So all these, so there's huge open questions that we have right now, and we're basically completely out of really, really good theoretical hints as to where to go to find, to, for example, build a new, some kind of experiment to discover that new thing. And it's really it's a bizarre crossroads right now, because we still have people in my field that were, they were educated and raised on this kind of like clockwork thing. It's like, oh, theory prediction, experimental verification. That's not what we have anymore. What we have is the possibility of discoveries showing up at very, very high energy colliders or lots of different types of experiments without any dedicated theoretical hints. And so for some of us, some of my colleagues think this is a little bit daunting. They're a little bit kind of nervous of this, but I think of this as kind of freedom, right? I mean, in a sense, we can think we have to recapture our species' kind of experimental, exploratory mindset, right? So that's what I'm not actually kidding when I talk about like a particle collider around the outer orbit of Neptune. Okay, obviously, it's probably not going to be Neptune. In fact, if you talk to my colleague Frank, who co-wrote the paper with me about the Moon Collider, he thinks you could be able to you could achieve the Plunk energy, this place where, that's actually the next guaranteed discovery, is at the Plunk energy. But again, you have to build an enormous collider. But he thinks you don't have to do Neptune. He thinks you could build a collider that circles around the sun, but only at 1/10 of the distance between the Earth and the sun. So totally doable, right? So we're at this really interesting crossroads right now, and I don't know what it's going to take for the next step forward. So that's why I can't actually answer your question in the sense of like, what's the next big thing? In particle physics, I have no clue, and that's both nervous, it's kind of nerve-wracking, and also really, really exciting. So the future is experimental, the future is exploratory, and we have no friggin' clue what's going to show up out of our colliders. And in fact, if we build a moon collider, if they build a moon collider, we'll all be dead by the time that happens. In the 22nd century, and they don't discover any new particles, guess what? That's a complete success, because that is information about the universe that we did not have before. It's a complete success. Every paper that we publish at the Large Hadron Collider that says, if you read it from one perspective, they did not discover a new particle. In fact, from another perspective, it says, we triumphantly ruled out a place in our data where there could have been a particle, and there is not now. So it's, again, we have to sort of change our mindsets from how a lot of us were raised as, what science is. And a lot of it, I mean, this is a much larger discussion. We can have the meta discussion about why we were raised this way too, right? Why do so many of us think of science as this kind of like clockwork thing that's supposed to give us discoveries, right? And in a sense, like a lot of us were raised with this sort of like great man theory of science, right? It's like a lone white male on a tabletop can change everything with a genius, brilliant insight. That's not the way science has ever worked, especially not now. So yeah, that's a long way back.
I'd love to have that
paper that was about a theory, and I didn't read the article. I guess you know about the theory. It's about living inside a black hole, and the big big bounce back of mass that is being compressed and then bounces back and creates another universe. Is it scientific or just bullshit? What are your thoughts?
Well, like I said, this is my kind of thing, right? The edges of science, where if you talk to the sort of like rational, sober scientists, no, that's bullshit. But I'm like, well, does it follow from scientific argument, but it just goes into kind of speculative territory that's still scientific? Then it's totally science to me. In fact, that is a great question, and in a longer version of this talk, in fact, I gave a version of this at the Royal Institution in London. I get a chance to talk about that. In fact, this is really great. So, you know how I said, you take your textbook on gravity and you find the black hole equation, right? It just tells, it's totally straightforward. It tells you if for some fixed amount of mass, how small of a volume you have to pack it in to make a black hole. This is when it kind of collapses, right? So for the Earth, you have to pack it in the size of a blueberry. You could do it for other things too. So if I wanted to make a black hole out of you, I would need to pack you into a volume that's smaller than, I think it's thousands of times smaller than the radius of a proton. And given the fact that that's even much, much smaller than our best possible length scale devices, measuring devices we can do right now, like the Large Hadron Collider, there's no way we'll make a black hole out of you. And also if I wanted to make a black hole out of a proton itself, right? Some of you may have heard, it's like, CERN is going to create a black hole to suck in the Earth. It's like, okay, number one, no, these are miniature modified versions of black holes. But even if you thought that was a possibility, just do the calculation yourself. We collide protons. If you wanted to make a black hole out of a proton, you would need to pack it into a volume that's several, I think 100,000 times smaller than the Plunk length. And given the fact that the Plunk length is the smallest physically meaningful distance scale that quantum mechanics allows us to define, there's no way that we're ever going to make a black hole out of a proton. But you can do it with other things too, like the sun. I think you'd have to pack the entire sun into a volume that goes around the sort of center part of Berlin. You could do that, I guess, without being a black hole. What about the observable universe? That's a pretty big object, right? So if I take the entire observable universe, and what I mean by observable universe is, basically this is a sphere centered on you that goes out as far as we can possibly see. Basically, you know that the universe is expanding. Yeah, you've heard this. And in fact, it's expanding so quickly, farther away from us that we get, there's certain things that have never had chance for a light signal to reach us yet. So there's sort of like this, you can think of it as a horizon, right? Like if you're standing, if you're like on a boat and you see this horizon, no matter how much you get to it, there's always a horizon there, right? So it's like, there's this place beyond which you can't see anything. That's kind of what's at the edge of the observable universe. There is a sort of edge to what we can possibly ever detect directly. The entire universe might be infinite. We in fact don't know how big the entire universe is. But the observable universe is totally calculable. We know that it's about, I think, 93 billion light years across. And we can actually calculate what the mass of the observable universe is. It's so cool. It's like something like 10 to the power 54 kilograms, right? And if you've ever gone on a diet, don't worry. If you think about that number, this is way, way better. Don't worry, you'll feel very good about that. 10 to the power 54 kilograms. So then put that into the black hole equation. Who's going to put it in the black hole equation? Okay, I'll give you the answer. In fact, if you put that volume, that amount of mass, the mass of the observable universe into the black hole equation, to make a black hole out of the observable universe, you would need to pack it into a volume that's already 3 times as large as the current observable universe. Okay, maybe I got that calculation wrong, right? So let's think about it. Maybe the mass estimate is off. Come on, it's a very large thing. I can't go to the edge of the universe and verify, what the mass density is out there. Maybe we got it wrong by, say, half. That's a big number. Like, maybe it's actually, 5 times 10 to the 53 kilograms or something instead. Okay, if you then put that into the black hole equation, to make a black hole out of the observable universe, you have to pack the entire thing into a volume that's still larger than the current observable universe. Do we live in an enormous black hole? The calculation is there. So this is an unsolved mystery of science, and it's completely irrefutable. You can just do the calculation yourself. But think about what it would mean if we were inside of a black hole, kind of like in the little sort of, the little kind of dramatic part here, right? For a large enough black hole, very contrary to what we learned from, science fiction movies and things, If a large enough black hole, if you went over the event horizon, you wouldn't feel anything. It would just be sort of normal. You could never go that other way. Like I said, it had this magical gravitational sensor that was telling you where you were pointing, right? If you tried to point it, out of the black hole, there's no such thing. Basically, once you get past this event horizon, there's no trajectory, even in principle, for you to ever end up somewhere else. But you could just end up within the black hole. You could kind of just like zoom around the sort of like the edges of it as well. As long as it's a long enough distance between the event horizon and the so-called center, the singularity, which probably doesn't exist, you could just live in a black hole for a very long time. And in fact, we could live in an enormous black hole too. Because think about what that would be for you inside of an enormous black hole. Like I said, you have this horizon idea. If you were in your spaceships, inside an enormous black hole, and you look toward what you thought was outside, you would always see this kind of horizon, right? There would be this edge, this kind of distance scale, beyond which you could never possibly see, and no matter how quickly you travel, you'd never be able to get to it. But it's also slowly growing larger. We know that black holes grow as they suck in more things, right? As black holes suck in more things, they grow very, very slightly. So basically, that's what you'd be observing if you're inside of a black hole, and this horizon, this edge of what you can observe is slowly getting larger and larger, but you can never possibly get to it. That's almost exactly what we experience right now here on Earth. We see out in space an edge. There's an edge to what we can observe, a horizon, the so-called cosmological horizon. And it's also always getting larger, right? Because as time goes on, a little bit more time will go on so that some of those stars or galaxies or whatever that are beyond the current horizon have suddenly had time for their light to reach us, so therefore our understanding of the observable universe gets larger and larger. But no matter how quickly we travel, we'd never be able to get to that edge. So that's why, in fact, this is kind of a wild idea that, it's kind of an unsolved mystery in a sense right now, because it's entirely possible. The question we have to figure out, which is related to your question, I promised a 30-second answer, that didn't work. Related to your question is that the thing that we didn't get a chance to talk about in this talk here is that thing at the center of a black hole. What is at the center of a black hole? So the mathematics say, right now, our current mathematics say that at the center of a black hole is something called the singularity, which is a point of infinite density and almost infinite curvature. I don't know about you, but I have no idea what infinite density and infinite curvature mean, and I'm a physicist. So it's probable that what happens is at the center of a black hole, there's new physics, new mathematics that we currently don't understand that step in to make sure that such a thing doesn't happen. Because it's likely that our universe doesn't use singularities. It doesn't make any sense. It's kind of like this other things. When our theory tells us that we have like infinite energy or probabilities greater than 1, it means there's something we're missing, right? So our universe, the black holes at the center, they probably don't have a singularity. But in some cases, in some theories, in fact, like you can find the solutions to these equations that have not just these Einstein-Rosen bridges, these wormholes, but the wormholes, like I said, could in principle be wormholes to other parts of our universe, but from other perspectives. In fact, they could be wormholes to other universes in a sense. And this is what finally answers your question in the sense that if we currently live within an enormous black hole, maybe the singularity is some sort of like abstract concept that doesn't really exist, and it's entirely possible that inside enormous black holes in our universe, those are actually birthing new universes, like ours, which is what we experience right now. And it possibly means that our universe was birthed from a black hole in another universe. This is entirely possible. It's also something right now that we have no way of testing. So again, this is where we kind of like I love to be on I love to be on chat shows and debates with like the sort of really sober rationalist scientists, because they're like, well, if it's not testable, it's not science, and we shouldn't talk about these things. Blah, blah, blah. And I'm like, no, it's totally okay, because it follows again from very logical scientific steps. You come to this conclusion where you're like, whoa. And for me, I would never be so kind of cynical to rule out the possibility that some future human will come up with a way to test this. Right now, we have no concept of what it means. I mean, what does it mean for me to like communicate with another universe? Like, this makes no sense, right? What if like the conditions of this universe are very slightly different from ours, right? Imagine right in front of me, opened up like a little wormhole magically, right? And it was like this glowing thing, and it's like, oh, you know what? You can, if you put your hand through here, you can interact with another universe. And I'm like, I'll take my measuring device and I'll put it through there. What if the other universe, carbon atoms don't exist? Once it goes back, it doesn't make any sense, right? So I don't even know what it means to communicate with another universe. The other part is that inside of a black hole, this notion of you going past the event horizon. We also, if you were your, say your great, 25 greats granddaughter is the person who does this, she needs to keep in mind that once she goes past the event horizon, she will learn a lot about the universe, but she can't get the information back to the rest of us. That's like that's a one-way trip as far as we know. So this is also what we have to keep in mind. So yeah, to answer your question, it's like these are the kinds of things that are grounded in a sort of scientific argument, but they get to the edge where they sort of edges of our knowledge that are kind of speculative, and that's where a lot of scientists, they start to get wobbly knees and freak out with good reason, right? Because there's bad versions of that too, right? Where I don't know how many times people have asked me after events, it's like somebody comes up, I really liked your talk, so what do you think about, can you see my quantum aura? No, yeah. So there's bad versions of the speculative science, but there's really good stuff too.
So that was like the black hole version of the 30 seconds answer.
It was.
Thank you very much, James.
I will be adding tomorrow. I'll be adding now, and I'm doing like a sort of a deep dive tomorrow at 11 too.
It's awesome. It's super inspiring to hear someone talk so passionate about his studies. So thank you very much for this finding tonight. Wir sehen uns morgen wieder hier auf der Republika. James ist noch ein bisschen hier.